The goal of this video is to motivate and define the notion of quotient ring, and we're going to pick up where we left off with the last video on ideals. So one thing to recall is that we can form Z mod n from Z by using this equivalence relation. We say that A is congruent to B mod n. And again, just as a reminder, this means that n divides a minus b, right? So our definition was that a is congruent to b mod n if and only if n divides a minus b. And we saw in the last video that this is just saying that a minus b is an nz, right? It's just telling me that a minus b is a multiple of n. We talked about ideals in the last video, and nz was an example of an ideal. And in fact, it was one of our motivations for the definition of ideal. Okay, so one thing to notice about this is we'll say that a is congruent to 0 mod n if and only if n divides a, which just means that a is a multiple of n. So in some sense, what we're doing with this equivalence relation is we're looking at our integers and we're setting all the multiples of n equal to 0. So we're setting all the elements of nz equal to 0. Okay, so last time we used this to define the notion of ideal of a ring. We kind of looked at some properties of nz and we picked out two of the properties, and we'll see today why these properties are important. So we said that I is an ideal if and only if, 1, I is a subring of R, and 2, I absorbs elements of R under multiplication. So what did that mean? That means that if R is an element of R and I is an element of my ideal, then I times R lands in my ideal and R times I lands in my ideal. And we saw last time that NZ had this property, but we also gave a few examples of other ideals. Okay, so let's kind of use all the information above to define congruence modulo I. So I'm going to let R be a ring and I be an ideal of the ring. And I'll say that two elements A and B are congruent modulo I. So I'll say that A is congruent to B modulo I if A minus B is in I, right? Just like up here, I said A was congruent to B mod n if A minus B was an element of nz. Okay, we'll write that A is congruent to B mod I if A minus B is an element of I. So this is going to be our definition of congruence. And now we'll prove various properties about congruence. We'll start with the fact that congruence modulo I is an equivalence relation. Okay, so this is going to be our first theorem, right? So just our definition is A is congruent to B mod I if and only if A minus B is an element of I. And we'll claim that congruence modulo I is an equivalence relation on R. So let's begin our proof. So we'll start with let A, B, and C be elements of R, right? These are generic elements of R. And I need to prove three properties, right? I have to show that this relation is reflexive, symmetric, and transitive. Okay, so let's start with the reflexive property. Let's start with reflexive. Well, I know that I is a subring, so 0 is an element of I. In that case, I know that A minus A is equal to 0 is an element of I. So I know that A is equivalent to A mod I. Okay, so I get the reflexive property. Next property we need to check is the symmetric property. So I'll say suppose that A is congruent to B mod I. Right. Well, then I know that A minus B is an element of I. And I know that I is a subring. So since I is a subring, I know that the additive inverse of A minus B is an element of I. But what is that element? Well, the additive inverse of A minus B is B minus A. So hence, B is congruent to A mod I. Right? B minus A is an element of I, so B is congruent to A mod I. Great, so this is symmetric. And finally, we can show that this is transitive. So I'll say suppose that A is congruent to B mod I, and B is congruent to C mod I. And my goal is to show that A is congruent to C mod I. Well, let's use our definition. Then I know that A minus B is an element of I, and B minus C is an element of I. I is a subring, so I can add these two elements, right? So since I is a subring, A minus B plus B minus C is an element of I. But what does that tell me? Well, A minus B plus B minus C is just A minus C is an element of I. So I could say hence, A is congruent to C mod I. Okay, and I've shown that congruence modulo I is an equivalence relation. The next thing we're going to want to show is that we can actually do arithmetic modulo I, just like we had arithmetic modulo n when we worked with the integers. Okay, so the next thing we're going to prove is that we can actually do arithmetic modulo I, just like we could do arithmetic modulo n. So I'll let R be a ring and I be an ideal of the ring. And I'll take 4 elements, A, B, C, D, and R, and I'll assume that A is congruent to B mod I and C is congruent to D mod I. Well, what we have as a consequence then is that A plus C is congruent to B plus D mod I, and A times C is congruent to B times D mod I. And the thing to compare this to is the earlier result that we proved when we were working with Z mod n, right? One of the early results that we proved was that if A, B, C, and D are integers, and n is a positive integer, and we assume that A is congruent to B mod n, and C is congruent to D mod n, then A plus C is congruent to B plus D mod n, and A times C is congruent to B times D mod n. And the whole reason we did this was because we wanted to define modular arithmetic. So the whole idea behind the next few theorems is to take all of our results on Z mod n and just generalize them to any ring, right? So it's kind of the motivation here. And we'll see in this step why having an ideal is going to be crucial. The thing to notice at this point is that in our last theorem, we didn't actually use the fact that I was an ideal. We only used subring properties of I to prove the last result, to prove that congruence was an equivalence relation. Okay, so let's start our proof. I'll write down our assumption that since A is congruent to B mod I and C is congruent to D mod I, then A minus B is an element of I and C minus D is an element of I. Okay, so let's see what we have. Well, one thing we might try to do is to add these two quantities, right? I know I is a subring, so I could say, okay, that means that A minus B plus C minus D is an element of I. In other words, that if I rewrite this, this is A plus C minus B plus D is an element of I. In other words, that A plus C is congruent to B plus D mod I. Okay, so the first property holds, right? The first property we get just by adding A minus B and C minus D. For the second property, we have to be a little bit more clever. And what we're going to do is we're going to mimic our proof from when we were working with the integers modulo n. Okay, so what I'm going to do is I'm going to look at, so I'll say also, if I look at AC minus BD, my goal is to show that AC minus BD is an element of I. That's what the second property says. How can I do this? Well, I'm going to be clever. I'm going to add 0 to the middle of this expression. So I'm going to write this as AC minus BC plus BC minus BD. Okay, and then what am I going to notice? I'm going to notice that, well, the first thing I could factor in a C out. So I'll write this as A minus B times C. And the second two terms, I can factor a B out. So I'll write this as B times C minus D. Okay, and what does that get me? Well, I know that A minus B is an element of I. So that implies that A minus B times C is an element of I, because ideals absorb under multiplication. I also know that C minus D is an element of I. So that tells me that B times C minus D is an element of I, because again, ideals absorb under multiplication. And since ideals are subrings, I can combine these two facts to say that A minus B times C plus B times C minus D is an element of I, right? So I get that this expression up here is an element of I. In other words, I've shown that AC is congruent to BD mod I. Okay, and so that completes the proof, right? And the one thing I want to point out here is that we have not used the fact that the ideal absorbs under multiplication until this very last step. So everything we did before this very last step would work for any subring, right? So the absorption under multiplication comes into play here. Okay, so now we can talk about equivalence classes modulo I, and we're going to change the notation up a little bit from our equivalence relation video. So the equivalence class, so I'll let R be a ring, I subset of R an ideal, and A be an element of R. I'll write A plus I for the equivalence class of A. And then the question you might have is, well, why the heck did I choose that notation? Why does that notation make sense? So let's explore this a little bit. The one thing I want to point out is that the old notation was we put A in a bracket like this, right? That was our old notation for equivalence class, and that was our notation for equivalence classes modulo n. The other thing I'll point out is that a plus I is often called the coset of a modulo I. So this is often referred to as a coset. So let's kind of begin. Why this notation? Well, let's start from the beginning. So the equivalence class of A is all of the B and R such that B is congruent to A mod I. Okay, so let's unpack this a little bit. Well, this is all the B and R such that B minus A is an element of I. Well, what does that mean? This is all of the B and R such that B minus A is equal to little I for some little I in I. Okay, well, if I rewrite the B minus A equal to little I expression, I get that this is all the elements B and R such that B is equal to A plus little I for some I in I. And then I could just rewrite this set. These are all the elements of the form A plus little I, where little I belongs to my ideal, right? So what does that tell me? That tells me that A plus I is really just A plus little I, where little I is an I, right? So I'm in some sense taking the elements of I and shifting them all by little a, right? I'm taking all the elements of my ideal and just adding a to all of those elements. So this notation is kind of, it tells us what the elements of our coset look like, or the elements of our equivalence class look like. The one thing we can do is we can compare this to Z mod n. So if I take A as an element of Z, one thing we showed when we talked about Z mod n was that the equivalence class of A was all numbers of the form A plus nj, where j was in Z. And one thing we might notice is that, well, this is just A plus all the multiples of n, right? So this is kind of where this notation, how this notation relates back to our old notation. Okay, so now that we've established the fact that we have an equivalence relation and the fact that we have some equivalence classes, we can use properties of equivalence classes to kind of say a little bit about these cosets that we formed. So first thing I'm going to do is I'm going to define R mod I, the set R mod I, and this is just a set of equivalence classes modulo I. All right, so this is just our set of equivalence classes. And what can I say about our equivalence classes? Well, going back to our equivalence relations video, we established a whole bunch of properties about equivalence relations. So now we can use them, right? We don't need to reprove them. We know that the properties we established about equivalence relations are true for all equivalence relations. So let's use those properties. Well, the first thing I know is that two equivalence classes are equal if and only if their elements are equivalent under their relation, or their representatives rather are equivalent under our relation. So what does that mean? That means A plus I is equal to B plus I if and only if A is congruent to B mod I. Another thing I know is that two equivalence classes have trivial intersection, so two equivalence classes are disjoint if and only if their representatives are not related with using our equivalence relation. So A is not congruent to B mod I. And then finally, I know that the ring R is just the union of all of these cosets. Okay, so this is just basic properties of equivalence relations. These are properties that hold for any equivalence relation. So in particular, they hold for our equivalence relation, the A is congruent to B mod I equivalence relation. Okay, so now we're ready to look at a few examples. So we'll start with a familiar example. So I'll let R be the integers and I be the principal ideal generated by 3. And so what does that mean? Again, that was just all the integer multiples of 3. It's all the, I look at my 3 and I take all the ring multiples of 3, right? So in this case, our ring is Z. So I'm just taking all the integer multiples of 3. So let's look at some of the cosets that we have. Well, the first thing I'll notice is, well, let's look at 0 plus I. 0 plus I is all elements of the form 0 plus little I, where little I is in my ideal. These are all just elements of the form 0 plus 3j, where j is in Z. And these are just all the elements of the form 3j, where j is in Z. And I might notice that that's just my ideal. So what I'm really saying is that if I take my ideal and add 0 to all the elements, I keep the same ideal. In our old notation, we just called this the equivalence class of 0 mod 3. It's the same set. We're just using a new notation now. What about 1 plus I? Well, 1 plus I, I'm going to take all my elements of I and shift them by 1. So these are all elements of the form 1 plus little I, where little I is an element of I. Well, these are all elements of the form 1 plus 3j, where j is in Z. And I might remember that, oh yeah, that's just the equivalence class of 1 modulo 3. And then finally, I can do the same thing for 2 plus I. I might notice that 2 plus I is 2 plus little I, where little I is an I. Well, these are elements of the form 2 plus 3j, where j is in Z. And we might notice that, oh, hey, that's just our equivalence class of 2. Okay, So what about the other equivalence classes? What if I tried to form something like 5 plus I? Well, I might do the same work and notice that this is the equivalence class of 5 mod 3, right? But we know that 5 plus I is equal to 2 plus I, since 5 minus 2 is an I, right? In other words, 5 minus 2 is a multiple of 3. In other words, that 5 is congruent to 2 mod I. Right, so if we try to form any other equivalence classes, we've noticed we've kind of captured them all. If I tried something else, I would notice that, for example, 13 plus I is equal to 1 plus I, since I know that 13 is congruent to 1 mod I, since 13 minus 1 is a multiple of 3. Okay, so again, all I'm doing here is I'm just defining Z mod 3, right? The set we called Z mod 3. The only difference now is that I'm labeling the cosets differently, right? I'm labeling the equivalence classes differently. So now we'll look at some more interesting examples. So we'll start with the ring R is R bracket X. So these are polynomials with real coefficients. And I'll take the ideal I to be the principal ideal generated by x squared plus 1. And again, all this means is it's all the polynomial multiples of x squared plus 1. So it's all the things in the form h of x times x squared plus 1, where h of x is some other polynomial. So let's kind of explore what it means for two polynomials to be congruent modulo I. Okay, so we'll say f of x is congruent to g of x modulo I. Well, what does this mean? This means that f of x minus g of x is an element of I. So let's unpack this a little bit. Well, this is just saying that f of x minus g of x is a multiple of x squared plus 1. It's equal to h of x times x squared plus 1. Well, what does that mean? That means that x squared plus 1 divides f of x minus g of x. So what we essentially have is that two cosets are equal to one another if and only if x squared plus 1 divides the difference of their representatives, right? So in some sense, I'm identifying two polynomials. I'm saying that f of x is equivalent to g of x if x squared plus 1 divides the difference of these two polynomials. Okay, so now we can explore a little bit about what this tells us, right? So I'm going to clean this up and we'll kind of explore some examples. Okay, so I've just cleaned this up a little bit, and now we can look at some examples. We might ask ourselves, well, what exactly is this relation doing? And remember, the thing we're trying to do is we're trying to make certain polynomials equivalent to other polynomials. Again, so we'll say that f of x and g of x are equivalent if x squared plus 1 divides their difference. So what are some consequences of this? Well, the first thing that I'm going to notice is I'm going to notice that x squared plus I is equal to negative 1 plus I, right? So in some sense, I'm saying that x squared and negative 1 are equivalent. So this is going to say that anytime I see an x squared, I can just replace it with a negative 1. Okay, so why is this true? Well, I know that x squared plus 1 divides x squared minus negative 1, right? I know that x squared plus 1 divides the difference between x squared and negative 1. Okay, so again, the idea is intuitively, we're setting x squared equal to negative 1 in some sense. We're forming the set where x squared is equal to negative 1. We'll see in a little bit that this actually has a ring structure, but we know that this is true for our cosets. Okay, so you might then ask, well, if x squared is somehow being made equivalent to negative 1, what does that tell me about x cubed? I might notice that x cubed plus I, well, what is this going to equal? This is going to equal negative x plus I. And why is that true? Well, I know that x squared plus 1 is going to divide x cubed minus negative x, which is just saying that x squared plus 1 divides x times x squared plus 1. Okay, so if I somehow make x squared and negative 1 equivalent to one another, I'm making x cubed and negative x equivalent to one another, which makes sense. So the next thing you might ask is, well, what about x to the fourth? What does x to the fourth become? The thing that I might notice is that x to the fourth plus I, this is actually going to equal 1 plus I. And why is that true? Well, it's true since x squared plus 1 divides x to the fourth minus 1. Why is that true? Well, I know that x squared plus 1, if I factor x to the fourth minus 1, this is just x squared plus 1 times x squared minus 1, right? So I see that one of the consequences of making x squared equivalent to -1 is that x cubed becomes equivalent to -x, and x to the fourth becomes equivalent to 1, right? So this is kind of the intuition behind this. I'm kind of making certain elements of my ring equivalent to one another, just like in Z mod n, I made n equivalent to 0 and then explored the consequences of that. We do have some more complicated examples. So I can look, for example, at 3x squared plus 2x plus 1 plus I. This is equal to 2x minus 2 plus I. Why is this true? Well, since I know that if I look at 3x squared plus 2x plus 1 minus 2x minus 2, what does that equal? Well, if I take this difference, I'm going to get 3x squared plus 2x minus 2x is 0, and then plus 1 plus 2 is 3. So this is going to be 3 times x squared plus 1. So this is an element of I, right? In other words, their difference is an element of I, or in other words, x squared plus 1 divides their difference. Okay, so I end up getting another consequence of this is that 3x squared plus 2x plus 1 is in some sense being made equivalent to 2x minus 2. So one thing we might recall about Z mod n is that when I'm working in Z mod n, or when I'm working modulo n, that any integer was equivalent to its remainder modulo n, right? Every integer was congruent to its remainder modulo n. And it turns out that something similar is going to hold for our polynomial rings, and we'll apply this to our previous example in a second. But what is our kind of general result? So I'll say let f be a field. Consider f of x to be any polynomial in the field bracket x, and consider the principal ideal generated by f of x. If I take any polynomial a in my field bracket x, then a of x plus I is equal to r of x plus I, where r of x is the remainder when a of x is divided by f of x. So in some sense, what is this saying? This is just saying that a of x is always equivalent to its remainder modulo f of x. Okay, so let's prove this, right? So this is the equivalent theorem, but now for polynomial rings. So let's prove this. So I'll say, okay, by the division algorithm, I can write a of x as f of x times q of x plus r of x for some remainder, where I know that the degree of the remainder is less than the degree of f of x, or the remainder is equal to 0. Right, it's the 0 polynomial. Remember, the 0 polynomial is not assigned a degree. Okay, so what does that tell me? Well, that tells me that a of x minus r of x is equal to f of x times q of x. Q of x is our quotient. And what does that tell me? That tells me that f of x divides a of x minus r of x. Or in other words, that a of x minus r of x is an element of I, or in other words, that a of x is congruent to r of x mod I, or in other words, that a of x is congruent to, or rather, sorry, a of x plus I is equal to r of x plus I. Okay, so this is a really powerful theorem because it allows us to reduce it allows us to figure out what our cosets look like. What are the possible candidates for our cosets? So let's apply this to our previous example. Okay, so at the bottom here, I've written our previous example. And what I want to do is get a sense of what all of our cosets look like. Well, so let's think about this. I know that when I divide by x squared plus 1, my remainder is either going to have degree 0 or degree 1, or it's going to be the 0 polynomial, right? So what do my cosets look like? Well, my remainders are all elements of the form a plus bx plus I, where a and b are in R, right? Those are all of my possible remainders when I divide by x squared plus 1. So these are all of my possible cosets. And remember, the idea is that anytime I encounter an x squared, I can replace it with a -1. Anytime I encounter an x cubed, I can replace it with a negative x, so on and so forth, right? So it kind of makes sense that this reduction gives us something like this. Okay, so now we'll consider a slightly more exotic example. So let R be the ring of all functions from the reals to the reals. And the thing to recall from an earlier video about rings was that this set R is a ring under the operations of pointwise addition and pointwise multiplication. So f times g of x is defined to just be f of x times g of x, and f plus g of x is defined to be f of x plus g of x. And what I'm going to do is I'm going to consider the set I of all the g and r such that g of pi is equal to 0. Okay, so first thing I want to do is check that this is actually an ideal, right? So I is an ideal. And we'll use our ideal test to do this, right? I want to kind of determine what the cosets of the set I look like. So let's first show that I is an ideal. Well, I is not empty, since we can name a function in I. G of x is x minus pi, is an element of I. This is a function that when I plug in x equal to pi, I get 0. Great, so this is not empty. Now I need to show it's closed under subtraction, and I need to show that it absorbs under multiplication. So I'll say let g and h be elements of I. Well then, if I look at g minus h of pi, this is going to be g of pi minus h of pi, which is going to be 0 minus 0, which is equal to 0. So I could say, so g minus h is an element of I. I have that it's closed under subtraction. And then finally, I can show that it absorbs under multiplication. So I'll say let f be an element of my ring R, and g be an element of my ideal. Then, if I look at fg of pi, this is going to be f of pi times g of pi, which is f of pi times 0, which is equal to 0. And I might notice that this is a commutative ring, so I only need to check one of the absorption conditions. I don't need to check both. So I can say that fg is an element of I, right? So I've proved that I is an ideal. Okay, so now let's explore what the cosets of I look like. So what I'm going to do is I'm going to take an arbitrary element of my ring. So I'll say let f be an element of R. Okay, I know that if I take an element of R, it's defined at pi, because these are functions that are defined from R and give back an element of R. So then I know that f of pi is going to equal some real number R. Right, so I know that f of pi is equal to some real number R. And I'd like to figure out what is f equivalent to modulo I. And it turns out that f is actually equivalent to a constant function. So I'm going to define the following constant function. I'm going to define the function c sub r of x to equal r. And this will be for all x and r. Right, so I'm going to define the following function. So this is the function that no matter what I plug into it, it just gives me back r. Okay, well, then what do I notice? I notice that f minus c sub r of pi, this is going to be f of pi minus cr of pi. So this is going to be r minus r. So this is equal to 0. So in other words, the difference of these functions, f minus cr, is an element of I. The difference has pi as a root, so to speak, right? The difference, the function I get by subtracting them, when I plug pi into that, I get 0. So hence, I know that f plus I is equal to cr plus I, right? So the way to think about this is that this function f is being made equivalent to a constant function when I form R mod I. So when I look at the set R mod I, this is just going to be the set of all C sub R plus I, such that R is an R. And then the thing you might notice about this is you might ask yourself, wait a second, is that somehow equal to the real numbers? Isn't that, just something that might be isomorphic to the real? So that's what we'll address when we talk about the first isomorphism theorem. It turns out that what we've created here is just a copy of the real numbers. This ring is just a copy of the real numbers in disguise. Okay, so we're finally ready to give a ring structure to R mod I. So what I'm going to define is, if I take any two cosets, how do I add them together? How do I multiply them together? And then we'll talk about, why does this actually make sense? Like, why are these operations well defined? And we'll talk about the ring structure of R mod I and do some examples. Okay, so I'll start with R is a ring, I is an ideal of R, and A and C are elements of R. And what I'm going to do is I'm going to define the sum of two cosets. I'll say A plus I plus C plus I is just going to be the coset A plus C plus I. So the coset of A plus the coset of C is the coset of A plus C. Similarly, I'll take A plus I times C plus I to be AC plus I. So the coset of A times the coset of C is the coset of A times C. Okay, so how does this relate to work that we've done earlier? Well, the thing to remember is to compare this to how we defined addition and multiplication in Z mod n. It's the same definition, except now I'm extending it to R mod I, right? And the thing to recall is that if A and C are integers, we defined the equivalence class of A plus the equivalence class of C to be the equivalence class of A plus C, and the equivalence class of A times the equivalence class of C to be the equivalence class of A times C. So now we're just extending this definition to all rings instead of just restricting ourselves to Z mod n. Okay, so before we discuss the structure of R mod I under these operations, we have to prove that these two operations are well defined. So the idea being that if I take two representatives of the same coset, so A plus BI is equal to, A plus I is equal to B plus I, and another coset, C plus I equal to D plus I, that no matter what representatives I pick, the sum comes out the same and the product comes out the same. That is that A plus I plus C plus I is the same as B plus I plus D plus I, and A plus I times C plus I is the same as B plus I times D plus I. So we need to prove that these operations are well defined. Okay, so let's do this. So I know that since A plus I is equal to B plus I and C plus I is equal to D plus I, we can write down that A is congruent to B mod I and C is congruent to D mod I. Well, what does that tell me? Well, I know from an earlier theorem that A plus C is congruent to B plus D mod I, and A times C is congruent to B times D mod I. So I know that those two are true. And it turns out these things that we're trying to prove are just going to be equivalent to these two true statements. So let's see why that's the case. Well, A plus C is congruent to B plus D mod I. I already know that this is true. This is equivalent to A plus C plus I is equal to B plus D plus I, right? So the statement about congruence is the same as the statement about equivalence classes. And that's the same as saying A plus I plus C plus I is equal to B plus I plus D plus I, because that's just our definition of our sum of cosets. So now we can do the same thing for multiplication. AC is congruent to BD mod I. I know that this is true by our assumptions. We know from an earlier theorem that this is true. Well, if I rewrite this in terms of cosets, this is just saying that AC plus I is equal to BD plus I. But by definition of multiplication, that's just A plus I times C plus I is the same as B plus I times D plus I. So this shows that our operations are well defined. And now we can talk about the structure of R mod I under these two operations. Okay, so we're finally ready to talk about the structure of R mod I. It turns out that R mod I is a ring, and now we've generalized the structure of Z mod n. So earlier we proved that Z mod n is a ring. We're going to use the exact same proof that we used for Z mod n, just appropriately modified to R mod I. So again, recall R mod I is the set of all cosets, A plus I, where A is an R, and we've just given it two operations. We've just defined what it means to add two cosets and multiply two cosets. So let's show that this is a ring. So the thing is, I know that closure holds by definition. Right? I know that closure under addition and closure under multiplication, those two are going to hold by definition. So I just need to check my properties. Like I need to check addition is associative, addition is commutative, I have an additive identity, I have additive inverses, so on and so forth. So let's go through and check these one by one. So I'll check that addition is associative. So how do I do that? Well, let's take three cosets. I'm going to take A plus I plus B plus I and add to it C plus I. Well, what is that? By definition, A plus I plus B plus I is just A plus B plus I. And then I'm adding to it C plus I, right? So I'm just adding the two things in parentheses using my definition of addition. And what is this? Well, I'm adding one coset, namely A plus B plus I, to another coset, namely C plus I. So that's going to be A plus B plus C plus I. And then I know that addition in my ring is associative, so I know that A plus B plus C is the same as A plus B plus C plus I. So I basically, I combine everything into one coset. I know that my ring is associative, so I use associativity from my ring, and now I'm going to pull everything apart again. So I'm going to say, okay, by definition of addition, this is the same as A plus I plus B plus C plus I. Well, what is this guy? This is just A plus I plus, and then in parentheses, B plus I plus C plus I. And so I've proved associativity. Okay, great. So now let's check that addition is commutative. So I'm going to take two cosets. I'm going to take a plus I plus b plus I. I know by definition that this is just a plus b plus I. That's what it means to add two cosets together. And I know now that a plus b, this is an element of R. And I know inside of R, addition is commutative. So I know that a plus b can be rewritten as b plus a plus I. And then I know that using my definition of addition, this is just b plus I plus a plus I. So I've proved that addition is commutative. The next thing we'll show is that the coset of 0, 0 plus I, is going to be the additive identity. So the ideal itself, 0 plus I was equal to I, we saw earlier, this is just going to be the additive identity. So let's check this. I know that a plus I plus 0 plus I, this is equal to a plus 0 plus I, which is equal to a plus I, right? So if I take the coset of a plus the coset of 0, I get the coset of a back. And I know since addition is commutative, that the coset of 0 plus the coset of a is also going to equal the coset of a. I can also check that we have additive inverses. So let's just do that real quick while we have the space. Well, for additive inverses, I know that if a is an R, then I know that negative a is an R. And if I look at a plus I, I'll use parentheses here just for clarity, then a plus I plus negative a plus I, this is going to be a minus a plus I, which is just 0 plus I. So I have additive inverses. So next I'll check that multiplication is associative. So let's try to write this down. I'll take the coset of A times the coset of B in parentheses times the coset of C. This is going to be AB, so it's the coset of AB, so it's AB plus I times C plus I. Well, what is this going to be? By definition, this is just AB times C plus I. And now what I know is AB times C, that's taking place inside of R, and I know inside of R I have associativity. So I'm going to move my parentheses now. This is going to be A times BC plus I. And once I've moved my parentheses, I'm now going to pull everything apart. So this is going to be the same as A plus I times BC plus I. And then I'm going to pull the BC apart. So this is A plus I times B plus I times C plus I. So I have associativity of multiplication, and now it just remains to check that I have the distributive laws. Okay, so let's check the distributive laws. I'll check one of them and I'll leave the second one as an exercise. The proof is almost identical, so it might be good practice. So let's look at A plus I times B plus I plus C plus I. Okay, what is this equal to? Well, I need to do the thing in parentheses first, so I need to combine B plus I and C plus I into their own coset. So this is going to be A plus I times B plus C plus I. So it's the coset of A times the coset of B plus C. And then I might notice that, oh, well, by definition, that's the coset of A times B plus C plus I. And then I'll say, okay, well, I know that this part, this A times B plus C, this is taking place inside of R, and R has a distributive law. So I can distribute those. So it's going to be AB plus I plus AC plus I. Okay, and then I might start taking this apart. I know that this is the coset of A times the coset of B. And I know that this guy right here is the coset of A times the coset of C. So let's pull them apart. So this is going to be A plus I times B plus I. And then the second guy is going to be A plus I times C plus I. And then I'll just say that the other distributive law is similar. So I'll leave that as an exercise if you'd like to try it. But it's the same proof. We're just putting A plus I on the other side. We're doing B plus I plus C plus I times A plus I. And finally, we'll have two quick corollaries. So one corollary is that if R is commutative, then R mod I is commutative. So if the original ring is commutative, then the quotient ring becomes commutative as well. And then the second corollary is that if R has an identity element, then the coset of the identity element is going to be the identity element of R mod I. So commutative rings stay commutative when we take the quotient. an identity element, its coset becomes the identity element inside of R mod I. Okay, so now we're ready to look at a few examples. Okay, so let's look at how this applies to one of our examples from earlier. So I'm going to consider the ring R bracket X mod I, where I is the principal ideal generated by x squared plus 1. So the elements we showed earlier are of the form a plus bx plus I. This is what our cosets look like. And let's kind of explore what this ring looks like or how this ring behaves. So if I were to do something, for example, I would take 3x plus 2 plus I plus, let's say I want to add to this 7x plus 1 plus I. The way I would add these two is I would just say, take this polynomial, add them together. So this is going to be 3x plus 2 plus 7x plus 1 plus I. And I see that, well, 3x plus 7x is 10x, and 2 plus 1 is 3. So I get 10x plus 3 plus I. All right, so this is the coset that I'm looking at. So pretty straightforward. Essentially, all I'm doing is I'm just adding term by term. This becomes more interesting when I do multiplication. So let's try to multiply these two elements together. So if I do 3x plus 2 plus I, and I want to multiply 7x plus 1 plus I. Okay, so what does our definition say? Our definition says just multiply these two polynomials together. So 3x plus 2 times 7x plus 1 plus I. And let's see what we get. We are going to end up with, well, it's 21x squared plus 17x plus 2 plus I. And the thing that we might remember from earlier is that x squared plus I is the same as -1 plus I. So anytime I see an x squared, I can replace it with a -1. So this is the same as 21 times -1 plus 17x plus 2 plus I. And what does this equal? Well, when I simplify this, this is going to be 17x minus 19 plus I. Okay, so I get something that looks like this. And you might ask yourself, wait a sec, it looks like I'm setting x squared equal to -1. And what that kind of reminds me of is complex numbers, right? I know that I squared is equal to -1 when I'm dealing with complex numbers. And if you've gotten the sense, then your intuition's kind of in the right place. So let's kind of look at how I would multiply two complex numbers together. If I were to take 3i plus 2 times 7i plus 1, let's see what this works out to be. When I multiply these out, I'm going to get 21i squared plus 17i plus 2. And I know that I squared is equal to -1. So this is going to be 21 times -1 plus 17i plus 2. And then I might notice that, wait a second, this guy right here is just 17i minus 19. And so it kind of looks like the multiplication I did in my ring, right? This in particular, this answer, this 17x minus 19, it kind of looks like the multiplication I just did in the complex numbers, right? Namely, 17x minus 19 looks exactly like 17i minus 19. So you might get some suspicion. You might say, oh, maybe this ring that I've just created is isomorphic to the complex numbers. I'll let you try this for other examples, but we'll see that the multiplication inside this ring looks exactly like multiplication inside the complex number. So in some sense, taking polynomials and making x squared equivalent to -1 gives us back a copy of the complex numbers. And we'll explore this in the next video. We'll actually prove that these two are isomorphic. Right now, we don't quite have the tools to prove it. Well, at least to prove it in a simple way, but we'll prove in the next video that this is actually the case, that these two rings are actually isomorphic to one another. All right, so our last example is an interesting one. So we'll consider the ring Z2 bracket X mod I. So I'm taking polynomials whose coefficients are elements of Z2 and quotienting it by I, and I is the principal ideal generated by x squared plus x plus 1. So something interesting is going to happen here. The first thing I want you to observe is that Z2 bracket X alone, this is the polynomial ring, this has infinitely many elements in it, right? There's we could list some of them. So 1, x, x squared, x cubed, x to the fourth, so on and so forth. So, and that list continues, right? X to the n, where n is bigger than or equal to 0. I have an infinite list of elements. So the polynomial rings are infinite. But when I quotient this ring, something interesting is going to happen. So I'm going to form Z2 bracket x mod I. And the thing to remember is that what I get is these are elements of the form a plus bx plus I, right? So this is all the possible remainders when I divide by x squared plus x plus 1. They're allowed to have degree 0 or degree 1, or be the 0 polynomial. And the coefficients a and b come from z mod 2. So if I start writing down this list, I might notice that, wait a second, there's only 4 possible elements. There's z plus I, 1 plus I, x plus I, and 1 plus x plus I. Those are the only polynomials of the form a plus bx I can write down if a and b are elements of z mod 2. I'm only allowed to use coefficients that are zeros or ones. Another thing that I might notice here is that x squared plus I is being set equal to negative x minus 1 plus I, but since I'm working in z mod 2, negative x is the same as x, and negative 1 is the same as 1, right? Because in z mod 2, 1 and negative 1 are the same. So what am I doing? I'm taking every instance of x squared and turning it into an x plus 1 inside of this ring. Okay, so let's look at some of the consequences of this. What I want to do is write down an addition table and a multiplication table for this ring. So the addition table is actually pretty straightforward, right? The idea being that 0 plus I plus 0 plus I is 0 plus I, 0 plus I plus 1 plus I is 1 plus I, right? We know that 0 plus I is the additive identity. So whatever I add it to, I'm just going to get the same elements back. If I do 1 plus I plus 0 plus I, that's 1 plus I. If I do 1 plus 1, that's going to be 2 plus I, but 2 is equal to 0 in z mod 2. So 1 plus 1 is equal to 0. 1 plus I plus x plus I is 1 plus x plus I. And 1 plus I plus 1 plus x plus I, that's going to be 2 plus x plus I, but 2 is equal to 0, so I end up with x plus I. And then I can continue similarly, right? X plus I plus 0 plus I is x plus I. X plus I plus 1 plus I is 1 plus x plus I. X plus I plus x plus I, that's 2x plus I, but 2 is equal to 0 in z mod 2. So x plus I plus x plus I is 0 plus I. And then finally, x plus I plus 1 plus x plus I, that's 1 plus 2x plus I, but 2 is equal to 0. So that becomes 1 plus I. And then I can fill in the bottom row similarly. Okay, so that's the addition table. Let's look at the multiplication table, but I'm only going to partially fill it in because I want to kind of demonstrate what's going on here. So let's look at the multiplication table. The first thing that I know is that 0 times any one of these elements is going to be 0. All right, so the first row is 0. And I also know that any one of these elements here times 0 is going to be 0. So this whole first column is zeros. All right, like 1 plus I times 0 plus I is 0 plus I. X plus I times 0 plus I is 0 plus I, so on and so forth. Okay, I also know that 1 plus I times any of these elements returns the same element. Right? I know that 1 plus I is the multiplicative identity. So 1 plus I times x plus I should be x plus I. Right? 1 plus I times 1 plus x plus I is 1 plus x plus I, so on and so forth. And then similar for the first column, if I do like x plus I times 1 plus I, that's x plus I. Right? If I do 1 plus I times 1 plus I, that's 1 plus I. If I do 1 plus x plus I times 1 plus I, that's 1 plus x plus I. Okay, so those are kind of boring. Those are not terribly interesting. What about some of the others? For example, what if I do x plus I times x plus I? I haven't filled this in, right? So let's kind of write this down. I'm going to do x plus I times x plus I. This is equal to x squared plus I. And I know that x squared plus I is the same as x plus 1 plus I. So this guy right here is going to be x plus 1 plus I. So I can fill this in, right? I could write this as, or I call it 1 plus x. So 1 plus x plus I. I can fill this in. Okay, what about if I take x plus I times 1 plus x plus I? Let's see how that one works. So if I do x plus I times 1 plus x plus I, this is going to be x times 1 plus x plus I. And what does that end up being? Well, that's x plus x squared plus I. And what does that equal? Well, I know x squared is equal to x plus 1 in this ring. So it's going to be x plus 1 plus I. So this is going to be 2x plus I plus 1 plus I, which is equal to 1 plus I. Okay, so what I notice is that this guy becomes 1 plus I. So the interesting thing here is that x plus I times 1 plus x plus I ends up being 1 plus I. Okay, and similarly down here, if I reverse the order of multiplication, I'll see that this guy is 1 plus I as well. Okay, finally, we have this last thing to fill in here, right? I need to do 1 plus x plus I times 1 plus x plus I. So let's do that really quickly at the bottom. So 1 plus x plus I times 1 plus x plus I. This is going to be 1 plus x times 1 plus x plus I. So that's going to be 1 plus 2x. 2x is 0 because I'm in z mod 2. So 1 plus x squared plus I. And what do I get out of this? I see, well, I know that x squared is equal to x plus 1. So this is 1 plus x plus 1 plus I. And I know 1 plus 1 is 0. So this is just x plus I. I know 2 is equal to 0. So I end up with x plus I. Okay, so that's our multiplication table. And you might be thinking, big deal, what's the point? So let me make some space at the bottom and I'll kind of write down what's interesting about this. Okay, so what's the interesting thing about this? The interesting thing is we've just constructed a field with 4 elements, right? Notice that every element has a multiplicative inverse. I know that the ring is commutative, and I know that 1 plus I times 1 plus I is 1 plus I. I know that x plus I times 1 plus x plus I is 1 plus I. So x plus I and 1 plus x plus I are both units. And so I see that every non-zero element is a unit. And so I've created a field with 4 elements. Why is that interesting? Well, up until now, the only finite fields we've had have been z mod p, where p is prime. So all the finite fields, the fields with finitely many elements that we've looked at, they've only had a prime number of elements. So we've constructed our first field with a non-prime number of elements. And we'll explore this a little bit more in future videos, but this is kind of a neat fact. Okay, and we'll stop here. The next video will be on the first isomorphism theorem, and the idea there is going to be, well, if I construct this quotient ring, is it isomorphic to any other familiar ring I might have seen before? So we'll explore those ideas.